Well, welcome everyone. This is Bill Gibbs. I'll be the moderator for this session today. I think we're in for a real treat as we hear from Dr. A.J. Perry on physics-informed machine learning, the next evolution in neural network development. And let me just talk about what we're going to be covering today and get right into this. We'll first talk just a little bit about capital, and then I'll give you some housekeeping or session pointers. Introduce the speaker, and then the bulk of our time together is a presentation with Dr. Perry. We'll allow a room for questions at the end of the presentation, and then talk a little bit about the two upcoming webinars. I'm excited that one of our webinar presenters for next year is with us, Dr. Reggie Freeman, and may even put him to work to tell us a little bit about what he's going to cover, but we'll see if we have time for that. And then finally, a little bit of the recording, slides, and certificate. I recognize in all of these webinars that many of the people who are joining our session are on the faculty or on the staff. They know about capital in a way perhaps that I don't even know. But for those few that might not be familiar with us, let me just go over two slides. They'll give you a little bit of an orientation to who Capital Technology is, what we stand for. We've been around for a long, long time, since 1927. So that means this decade, in just a few years, we'll be celebrating our 100th anniversary. We're one of the very few private universities in the state of Maryland, and for that matter, almost anywhere in the country, that is specifically devoted to STEM, engineering, cyber, computer sciences, and the management of technology. And that makes us very good at what we do, because we don't do it all. We try, but we focus on these areas, and I think you'll see that as we hear the presentation today. We're nonprofit, private, and accredited. Each of these are potent and important terms, but I want to spend a little bit of time just on the accredited one, because there's so much confusion about accreditation. And I know that some of our viewers today are not from the United States. In the United States, universities are reviewed by accrediting agencies that are called regional accreditation. Regional accreditation, not national, but regional accreditation is the highest level of accreditation available to any university in the United States. And that is what we have. We're accredited with the regional accreditation with the Middle States Commission on Higher Education. We're also authorized by the state of Maryland, where we're located. We're located in Laurel, Maryland, just outside of Washington, D.C. The state of Maryland allows us to confer degrees all the way from the two-year associate's degree right up to the doctoral degrees. And I'm very pleased that we have Dr. Perry today, who is an alumnus of the school with one of our PhD programs. I'll introduce him in just a moment. Just a little bit of housekeeping. We'll answer questions at the conclusion of the presentation. At any time, you can post a question in the text chat. That was why it's so important to make sure I had it activated. And we'll answer as many of those questions as we possibly can in the hour that we're together. We're not activating microphones or webcams for participants today, so that the way we want you to communicate with us is via the text chat. We'll make sure a link to the recording as well as to the slides are sent to all registrants, and they'll be available on our webinar webpage next week. A participation certificate is available by request, and I'll tell you how to get that at the end of the presentation. That participation certificate is available both to our live audience today and all those that watch this on demand on recording later. With that, I want to get right into the presentation and give our presenters just as much time as possible. Dr. A.J. Perry will be talking about physics-informed machine learning, the next evolution in neural network development. A little bit about the presenter, and I'm going to read this, make sure I cover it right. Dr. Perry served 22 years in the U.S. Army as a Ranger and a Special Forces soldier, and is currently a senior data scientist in the public sector. He's also the doctoral dissertation chair in artificial intelligence for Capital Technology University. So for those of you that go into this field of machine learning or artificial intelligence at a PhD level, he would be the person supervising that academic program. Dr. Perry holds a Bachelor of Science in Psychology from Ottawa University in Kansas, a Master of Science in Data Analytics from Southern New Hampshire University, and a PhD in Artificial Intelligence from Capital Technology University. His research focuses in the area of statistical relational machine learning, relational quantum mechanics and quantum machine learning, and probabilistic graphical modeling theory. And I've had to practice to say all of those, especially that last line. I also want to mention that Dr. Perry stresses the need for a wider understanding of the broad technological implications associated with artificial intelligence. He works closely with a veteran population after many years serving in the U.S. military, and as well as underrepresented rural and urban communities. With that, I'm going to give control to Dr. Perry. He is going to run his own slide deck, so bear with us for a moment as we transition, as I stop my slide share and he moves into share his.
Thank you very much, Bill. I appreciate it. You've been instrumental in getting this thing set up. I couldn't have done it without you, that's for certain. Folks, bear with me for one second here while I get the slide deck set up and ready to go.
In the event that you can't get yours to operate, I'll give you control. There we go. It looks like it started. Excellent.
Yeah.
Good.
Okay. Thank you. Fantastic, everybody. And actually, what I'll do is I'll take myself out of the picture here shortly, so you're not distracted by me, and you can pay more attention to the slides if you prefer. But I won't let that stop the train from going. Actually, we'll just start with what we have right here. As Bill was so gracious to introduce me with the physics-informed machine learning, the next generation in neural network development. And that's a little bit of a question mark, because a lot of folks, a lot of practitioners, a lot of engineers and modeling experts in machine learning would tend to argue with that. But that's part of the reason why I'm presenting this presentation today, is to give you a glimpse into this very interesting approach of modeling machine learning, or actually developing machine learning models using the physics-informed approach. A quick agenda overview, and these are the things that we're going to be talking about mostly, and I'll go into more detail with this later. What is physics-informed machine learning? Okay, and what is its utility? The foundations of physics-informed machine learning, physics-informed machine learning in action, recommended individual development environments. Excuse me. So we'll talk about that more in depth later, but really there's a litany of software stacks out there used to process and develop a lot of these machine learning models. And then we'll talk about what's next for physics-informed machine learning. And then we'll jump into some related links that I think are going to be interesting to the crowd, some works that we have in development, contact information for those that are interested and are reaching out to me and getting more further glimpse into what I'm doing. And then we'll entertain questions. We'll do a Q&A like Bill said, and then of course there's some references at the end. Quick disclaimer, quick housekeeping note here. The opinions expressed in this presentation are solely those of me and are not those of any affiliated institutions or organizations. All right, physics-informed machine learning. What it is, and what's its utility? Physics-informed machine learning is really a derivation of scientific machine learning, or what we can think of computational machine learning. And this technique emerged approximately about the end of the second AI winter. And let's hope that that's the last AI winter. And that happened around the mid-90s, and that's the estimate for that. Applying this method in development, for instance, I'll give you an example. When building a classification model, say your typical feed-forward neural network, this approach has a lot of utility in being able to approximate or being able to assist individuals or the developers in approximating what the model's output is going to be. And those of you who are those of you that are familiar with machine learning know that approximation is all of what machine learning is about, sort of getting as close to the approximation as possible before actually going into a next step. And physics-informed machine learning tends to have more utility as of now in the hard physical sciences, astronomy, chemical, and engineering technologies. And the reason I want to put a lot of emphasis on engineering technology is because a lot of the engineers have developed these techniques for physics-informed machine learning to come into the fold as it is now. Also, physics-informed machine learning and deep learning, in particular, has a very strong impact on simulating the attributes of a physical state. And I'll give you a quick example. Think of something along the lines of the physical state of let's see here. Pardon me. I'm running a blank for a second, but any physical state that you can think of. Okay, any physical state that can be articulated mathematically using ordinary differential equations, or in this instance, partial differential equations. Okay. In addition, research is emerging using physics-informed machine learning, which is distinctly separate from the physical sciences. And what I mean by that is typically the physical sciences very often have information out there, mathematical problems and theories that have already been tested, that are being worked on now, that there are a lot of information and a lot of research that has been done on these partial differential equations. Well, other sciences, some of the hard sciences, in addition to some of the softer social sciences, so to speak, are starting to explore ways, or researchers are starting to explore ways of how to actually mathematically explain these systems. And anything that can be explained mathematically using a partial differential equation or an ordinary differential equation in some instances can actually be implemented into the hyperparameters and the parameters of a neural network. And that is the real value in how physics-informed machine learning is assisting the development of the neural networks. And these other applications that I briefly mentioned involve some of the social sciences, sociology, psychology. There's a lot of interest that is starting to come out of that. And in addition to that, there's another approach that is emerging in addition to using partial differential equations, is using a type of differential equation, or excuse me, a type of partial type of PDE from a stochastic perspective or from a nonlinear perspective. And we can talk about that more later. PDEs really are the foundation of scientific machine learning. And this foundation, again, was created and sort of generated by a lot of early researchers in AI and machine learning, and has really sort of been adopted by a lot of folks in the engineering side of the house. As I may have mentioned before, PDEs mathematically describe the states physical states, and the ability to go in and estimate the parameters of a machine learning model and save a lot of time computationally. And as far as the energy consumption that a lot of these large language models do require at this point. So being able to estimate is, again, a central premise of using a PDE. Some of the more popular PDEs out there, partial differential equations, come from the older or the more well-known more well-known equations that are out there. Brownian motion, Schrodinger's equation, is wave equation, Helmholtz, Stokes, and many others. There are different portions of these equations that can be used. They can be cross-pollinated. So basically, the utility of these equations are really only limited to the imagination of the researcher and the ability to prove that theory, right? So there is really, at this point, there is very little limitation that is out there for a researcher to be able to go in and actually attempt to solve some of these problems. Okay, key to really implementing a lot of these PDEs into a machine learning model is understanding the physical characteristics, okay, of a given system, and then translating those physical characteristics into a property of a hyperparameter that applies to that machine learning model. Okay, and as I said before, arguably these theorems are only limited to the known physical laws and the proofs that the researchers can actually prove. And this is just a brief snapshot of, I guess I just wanted to give everybody sort of a glimpse into a universal differential equation and how some of these things may apply. I'm certainly not expecting anybody to remember this stuff, but this is, again, just a snapshot. You know, and performing these, you know, a lot of these equations clearly involves calculus, which is the central premise of a PDE, and then being able to go in and solve these things is really dependent on the researcher's understanding of, one, what the purpose of that machine learning model is supposed to satisfy, and how the physical state can be translated into the parameters of that machine learning model. Okay, and this above equation really is just the genesis of something that I've been working on in a recent piece on a different approach to using, say, a forced stochastic delay PDE in order to use that PDE and embed it to get a bigger, a broader set of approximations, right? So this example is really focused on a UDE, which is using a function of time. Okay, a function of time is basically something that a portion of the physical system that can be applied to almost anything, right? So any system, any physical system that is in a third dimension or has three dimensions typically has a function of time that it adheres to. So this is just an example of that. And there are some other processes, the Winner process and the Levy process, for instance, that can be superimposed into this partial differential equation for a further analysis, and then moving that development forward. Now, there are some things very important consider when it comes to the development of these machine learning models. One of the critical aspects from what I've seen in my research is the explainability part, or the explainability portion of an algorithm that is driving a set of algorithms, or an algorithm that is driving a machine learning model. I think explainability is probably becoming more and more important, and will become more and more important as these models grow in size, as these models become more ubiquitous throughout society and the way we use things. I mean, right now they're an extension of us. They're everywhere. Data are being collected on all of us, either directly or inadvertently. So it's really incumbent upon all of us as a society to be able to explain and not just the purpose of a lot of these machine learning models, but how we arrived at those conclusions. Okay, and one way of doing that, and this is just again a shell, is using a process called CRISP-DM or ASM-DM. So basically, CRISP-DM and ASM-DM are very much related. It's an analytic approach to machine learning and predictive analytics. So being able to explain how your model is developed using a lot of these methodologies, I think, is becoming more and more critical as we move into the explainable AI framework. And this is just another illustration of an output that I think we, as researchers, have to be very studious in presenting as we develop these models, and we provide these outputs to a broader crowd of what they're actually intended to do, what they are doing, and not just necessarily the operationalization of a model, but how we arrive to those conclusions. Those conclusions are of more and more importance. Now, this is Dr. Craig Ginn. Dr. Ginn is a professor out at the University of Washington, and he and his team put together a very, very interesting explanation into the development of a deep learning model for global coordination transformation. All right, and I'll let him explain a little bit of this. It's a long video, but we're only going to look at the first 2 minutes of it, just to give you an idea of how a lot of these PDEs are being implemented. And this is specific to his team's needs. So I'll just play this little short minute clip for you.
AJ, you may need to reshare with sound.
Okay.
Yeah, Dr. Perry, you'd have to actually stop sharing your screen on Zoom. And then when you go to reshare it, you'll see at the bottom there's a little checkbox to share the audio as well.
Okay.
You just check that off, and then it'll share the sound from the video.
Okay, thank you. Thank you.
While he's doing that, shout outs to Joe Lara, who is our technical consultant. Thank you, Joe.
I thank you.
You folks, just bear with me 1 second. I'll get this thing squared away. Okay, I think we got it now, Bill. I'll go ahead and hit start.
Yeah, you're good now.
You got it? Okay.
In this video, I'm going to talk about our paper, Deep Learning Models for Global Coordinate Transformations that Linearize PDEs. This appeared in the European Journal of Applied Mathematics in a special issue on connections between deep learning and PDEs. So I'm Craig Jin. This is joint work that I did with Bethany Lush, Steve Brutton, and Nathan Kutz. All right, so let's start with what's the goal of this work? What we wanted to do is we wanted to create a method that we could use to discover coordinate transformations that linearize PDEs. So sort of the general outline of what we want our method to do is, let's say we start with some function u that's governed by a nonlinear PDE. What we want is some coordinate transformation from u to v, where this new function v is governed by a linear PDE. So we wanted to have linear dynamics for v. So why do we want a linear PDE? Well, there are already many well-established methods that work for linear PDEs. So as some examples, we're really good at doing things like estimation, control, and uncertainty quantification in the context of linear systems. All right, so this allows us to do all those kinds of things. And in particular, we also often for linear PDEs have things like exact solutions, or even if we can't write out the exact solution, we can do an eigenfunction expansion and then easily evolve the system forward in time. So when we have this linear PDE, we can easily march forward in time from time t to t plus delta t. And then if our coordinate transformation is actually invertible, well, then we can invert the transformation and we have our solution u to the nonlinear PDE at some time in the future. Okay, so we want to try to emulate this procedure here. So one question that might come to mind is, how do we know if there is a coordinate transformation? If we have some nonlinear PDE, how do we know whether you can linearize it with some transformation?
Okay, folks, the reason I wanted
to the mathematical theory.
The reason I wanted to show you that video clip, and I hope it was useful, is just to give you a glimpse into some of the utility that is available out there, and that a lot of these physics-born machine learning approaches are good for. And as you can see, Craig Jin and his team had a very specific question that they were trying to answer, or a very specific problem that they were trying to solve. And they were able to do it with a lot of explainability in this. But as you can see, it wasn't simply just one approach. They did use multiple PDEs and combined a lot of the functions in different PDEs in order to answer those questions, in order to sort of linearize their coordinates. Transform the coordinates. So this is just one example of many that are out there, and many more, I'm sure, are emerging. There tends to be a very wide and deep research and development arm in a lot of the national laboratories that are using PDEs to solve some almost intractable problems. So again, there's a lot of utility in this. This is just a recommended software stack that I'd like to share with everybody. And the reason this software stack, I think it's useful, is because this illustrates a variety of libraries, some from Node.js, some from Python, some in R. There's no libraries in R on this one, but these packages and these software stacks, again, they're growing open source community. There are more and more folks, more and more researchers, more and more just regular people getting involved in this and making their contributions. So the community is growing far and wide. So we can expect, as we continue to develop these machine learning apparatus and modeling and get better and better at it, we can expect more and more relevant packages and more relevant libraries to make appearances. And just just to answer this question right off the bat, I prefer to use R and Python when it comes to this type of thing, but that's just because I'm more familiar with that. And lastly, I would like to share with everybody just a couple of useful links that I found interesting. One is Craig Jen's brief. You can view that thing in entirety. There is another one out there. There's not very much on YouTube about this kind of stuff, but there is more and more emerging. I think the Rethinking Physics-Informed Machine Learning Neural Networks is a very good video. And also there are a lot of resources from the PNNL laboratory out in the Pacific Northwest, where that research lab is producing and publishing a lot of their research strictly dealing with these physics-informed neural networks. Now we do have a few papers pending here. We have one preprint, plant breeding and biomolecular classification in quantum Bayesianism, physics, informed machine learning, or physics-informed neural network architecture. I know that's a mouthful, but it's a relatively short brief. Really, it's a short brief, and it's just giving a glimpse into how some of these approaches can be used specifically in a plant breeding environment for any plant breeding researchers that may be out there. An upcoming paper is a metadata causal inference of concept drifts in statistical relational machine learning. Now that's a very interesting piece that I hope will be done here shortly, and I'm working on that with Dr. Cope, Dr. Robinson. You folks may know Dr. Cope and Dr. Robinson from Capital Barbacary, and I'm giving you advice from some other people, some other researchers out there at this point. And the last paper that we're actually working on currently is scientific and probabilistic approaches to the quantification of human capital management, how machine learning is advancing human resources. Now, this is interesting because what we're trying to prove in this is how the human element can be quantified using partial differential equations. And these things can be applied in a human capital management approach, right? So a non-physical system, meaning the human element, that we encapsulate and use and theorize in mathematical terms using partial differential equations, that we can then articulate to a human capital management or human resources management environment on how to implement some of these things and do better predictive and prescriptive analytics for the human capital management arena there. And also you can see at the bottom left-hand corner, my contact information. Feel free to reach out to me anytime if there's any questions, any suggestions, anything that you'd like to speak about with statistical relational machine learning, or more specifically, physics-informed machine learning. And then at the very bottom, you can see my GitHub repository, the link to my GitHub repository, or GitHub repository. You can see a link there. Feel free to take a look at that. I keep most of that stuff open source and forward facing. So feel free to take a look at that. You can fork that stuff. You can fork other repositories and sort of make them your own. Feel free to share anything with me that you see that's relevant to my repositories in GitHub. And at this point, I guess we can move Bill right into the Q&A.
Sounds good. Thank you very much. Before we start the Q&A, let me remind everybody that if you have a question, comment, that just post it into the text chat. We'll answer as many as we can. We're doing well on the time, and so we have plenty of time to answer these. I wanted to just make a comment here. I find it interesting in your list of papers that you're working on or that are upcoming. Everything from plant breeding to human resources. It's an amazing array. I mean, that scientifically, that is a very broad swath of work that machine learning could impact. Okay, I'm going to start with the first question here. First, let a shout out to Andrew, who says Dr. Brunton's PhD students are working on a lot of PIML projects. They're super interesting. Just wanted to thank you, Andrew, for commenting on that. Doug Tran says, I'm a data scientist PhD at Capital. Thank you. Doing research on deep learning NLP. Is anyone here familiar with that, with NLP? So since you're the presenter, I'll ask you first your level of familiarity with that.
Sure. Yeah. Natural language processing, I think, is probably one of those emerging subcategories of artificial intelligence, and particularly machine learning, that is really making an impact socially. I mean, natural language processing with the large language models, which we see from Google and from Microsoft and from other big tech companies that are out here providing or illustrating a lot of text to image. You've probably seen some of the recent news and publications on a lot of this AI generated art, right? This is text to image artwork that is being fed into a large language model. I mean, that's just one application of natural language processing that is showing a lot of utility now from a perspective of art. Okay, natural language processing is certainly doing a lot when it comes to the large corpus of text data that's out there, and evaluating that, sentiment analysis, topic modeling. I mean, it goes on and on and on. And a lot of these algorithms that are being used are algorithms that have been developed, back in the 50s and 60s. So a lot of these things have been developed back then, and they're just really showing more and more utility now as people are starting to understand the different applications for them. So I think NLP is probably one of the most fascinating and utilitarian portions of AI and ML.
Thank you. Gomez asks this, maybe Gomez, I'm sorry. Can you share your upcoming papers with us? Are they available online? So that may go back to your GitHub if I'm not sure these particular papers are there yet. But if they were to visit your GitHub site, what would they find?
If you visit my GitHub site, what you'll see is several repositories of different approaches and code script that's related to a lot of the projects that I have and other projects from researchers that I collaborate with. As far as the availability of the papers, what I'd like to do is make preprints available so I can get feedback and ideas or suggestions from other researchers out there before we actually submit, or before I actually submit these papers for official publication. So the only paper that is in preprint right now is the on Earth Archives, the paper on plant breeding. So if you'd like to take a look at that, and that's really sort of a primer, but if you'd like to take a look at that, I can certainly post a link at some point to the location of that paper. But if you go, if you were to go to eartharchives.org and just type in the title of that paper, then it will pull up right away. So you can take a look at it. But again, the other papers are going to be in preprint at some point here in the future.
Okay, thank you. Andrew asks an intriguing question. He says, would you consider a neural network that uses field equations instead of a linear equation for their activation function to be PIML
That's a great,
instead of a
right.
generic PDE?
Yeah, that's a great question. I think it could be. I think it definitely could be classified as a physics-informed machine learning apparatus because you're using the activation function, right? And the activation function is just one of many activities, as you know, within a neural network architecture that is making some sort of is drawing some sort of conclusion. So absolutely, I would say that that an activation function that's inspired by some physical law would certainly be classified as a PIMO.
All right, thank you very much. Andrew makes a comment and then a question. I think it's worth reading the whole thing. The capital management aspect is interesting. I work in the public sector. We were always challenged with manpower management with respect to recommending IT solutions and trying to estimate manpower impact. I will be interested in following this progress. And then he has a question. Any observations, predictions on potential impact quantum computing might have on machine learning?
Great question. Absolutely great. I would actually have to divert to one of my colleagues, B. Carey, on the human resources side. She's the expert on that. But as far as what quantum mechanics or quantum computing means for the machine learning world, the impact that it may have, I think it may have multiple impacts. Now, Dr. Steele at Capital is very much an expert on that, and I often ask him. I've reached out to him before for his perspective on the influence of quantum mechanics on artificial intelligence and machine learning. But I think we won't necessarily see an abrupt change. I think it'll be more of a gradual change as far as what quantum mechanics or what quantum computing and the marriage, I guess you could say, of quantum computing and machine learning will actually do. That will probably be more in the research and the research and development side with the national laboratories and a lot of the private sector tech companies before we see as a population or as a society, before we see a lot of the utility in that. Because right now we really don't need, socially speaking, we really don't have a need for a quantum processor, right? We can handle all of our computational challenges usually, from an average social aspect with the classical systems we have. But I think at some point in the next 10 or 15 years, the next 5 to 10 years, we'll probably see what that difference is and what impact quantum computing is having. Well, quantum computing and machine learning coupled are providing, different than a classical approach.
All right, thank you very much. I don't see any additional questions. I'm going to put out one more call for questions or comments. These have been very good. Thank you. I appreciate those. But we'll want to just give a moment, and then if not, we'll move on. Okay, let me remind everyone that the copy of the slides and a copy of the recording will be sent to everybody who registered today. And let me move ahead. I'm going to go ahead and share my screen one more time so that we can and these are the references that Dr. Perry has mentioned, and again, they'll be available to you. Now, let me just go ahead and talk a little bit about our upcoming webinars. I also want to see if Dr. Perry is still on board. I'm going to allow you to talk, Dr. Perry, if you don't mind. I'm putting you tremendously on the spot. We have webinars coming up after the first of the year. On January 19th, Dr. Reginald Freeman, who is, I said Dr. Perry, I meant Dr. Freeman. Dr. Reginald Freeman is on the call. He'll be talking about transformational leadership, leading and following from the front. I have given you mic privileges, Dr. Freeman, if you're available. We'll see. I'm putting you on the spot because I had not done that before, but go ahead and just tell us a little bit about what you intend to cover here in the January webinar.
Well, thank you so much, and good afternoon to those on the East Coast, and good morning to my fellow Best Coast, aka Left Coasters. Truly looking forward and excited to our discussion on January 19th as we talk about, as the title indicates, transformational leadership, leading and following from the front. And so from a fire and emergency services perspective, I look forward to talking about the fire service hierarchy, our traditions, as well as maybe even some impediments to true empowerment. And although it's being delivered from a fire and emergency services perspective, it's truly applicable to any profession, whether it be private or the public sector. And that's going to be followed up with talking a little bit about emotional intelligence, or looking at one's emotional quotient when it's combined with true transformational and servant leadership principles. So we'll talk about Bass's theory on transformational leadership from 1985, and then of course Robert K. Greenleaf, the founder of servant leadership, from a faith-based essay that he wrote in 1970. So EI, servant leadership, transformational leadership with identified organizational goals and objectives. They can easily be obtained if there's true synergy amongst all the aforementioned. And then of course, last but not least, we'll talk about enhancing efficiency and effectiveness, as well as understanding the difference between climate and culture. A lot of times we always talk about culture, but we forget about the precursor to culture, which is climate. And so going to be dynamic, going to be energetic, because I will have my mocha with 3 shots of espresso by the time we have our discussion, and hope that you will be able to join us on January 19th. Thanks so much, Doc.
Thank you very much. I had taken my video off, otherwise you would see me laughing about the shots of mocha. Okay, excellent. Now you'll notice a theme here coming up with the second webinar with Darren Dillow in February, occupational safety health emphasis on mental well-being. Dr. Dillow will discuss a very important topic. We've done so much with creating a safety environment in the workplace, but now we're beginning to discover the importance of mental health in the workplace. And that becomes very important as we look at leadership. So these two really are complementary to each other. I encourage you. We'll be sending out information about all of those. And Dung, I see that you have a question. I'm going to finish my little section and go right back to Dr. Perry to answer your question, and then we'll conclude. To register for any upcoming webinars or to view any webinar on demand, just simply go to captechu.edu/webinar-series. This is my final slides. I just want to mention that a copy of the slides and a link to the recording will be sent to all registrants. And so watch for that email. When you get the email, you'll be invited to receive a certificate of completion or attendance. It's available upon request. Simply wait till you get the email and then reply to the email with the name that you want on the certificate, and we'll be happy to supply that to you. Now I'm going to return to Dung Tran's question. He said, I'm interested in a different type of deep learning model. What types of DL models do you work with mostly? Transformer, RNN? I'll leave that over to Dr. Perry to answer that question.
Sure. Thanks, Bill. That's a great question. My modeling deals primarily with probabilistic neural networks. So a probabilistic deep neural network, it's multi-layered, multifaceted, specifically an extreme learning machine approach. And if you aren't familiar with extreme learning machines, this is an architecture that has a lot of utility when you're looking at data types that may have sort of issues of data set shift or concept drift. Okay, so the extreme learning machine is inherently a deep neural network, and it can apply probabilistically. You can have a deterministic deep neural network. You can have a number of configurations based on your need. But my development is typically from a probabilistic perspective, as opposed to a frequentist perspective or deterministic. But again, you may want to consider taking a look at some of the extreme learning machine architecture for a deep neural network. And if you have any questions, feel free to reach out to me via email, and I'd be happy to point you in the right direction.
Thank you very much. And I think that with that, I don't see any more questions. I do see a comment from Dr. Freeman. Thank you for your service to the country. I'd like to thank not only Dr. Perry, but anyone who has served with our U.S. military. Thank you for what you have done for us. With that, I want to go ahead and we will close out the session today. We're right on time. It worked out well. I'd like to thank our presenter. Joe Lara has had to drop off the discussion, but I would like to thank him for being our technical consultant today. And again, I've said this before, but one more reminder, I will be sending a copy of the slides and a link to the recording to all of the registrants. We actually had well over 100 people register for this session today. And so I'll get that over to you. Thank you very much for your time, and you all have a good day. And with this, we are officially done. And thank you, Dr. Perry.
Thank you, Bill. Thanks, everybody.